Yeah, thank you very much for the nice introduction and for the invitation to speak. I noticed you had many high caliber speakers in the seminars, so it's a big honor to be here myself. Sarah already said the title, Group Invariant Machine Learning, Fundamental Domain Projections. So I'll start by introducing the bit silly toy example that I'll follow throughout this talk. But bear with me, at the end there will be actual examples of where we applied this technique. So the toy example is S3, the permutation group of 3 elements. This acts on R3 by permutation of coordinates. So for example here, this 1-2 permutation in cycle notation switches the first 2 coordinates. And it's perfectly fine to think of that as some combinatorial gadget, but there's some actual geometry happening, and we'll later need the fact that these are isometries acting on Rn. And we're interested in group invariant machine learning, and functions are group invariant if they satisfy this equation here. So f of g times x equals f of x. And so the toy example within the toy example is an example of a group invariant function, the maximum function, which takes a vector, a 3 vector, and maps it to its maximum. And now, the reason this toy example is a bit silly is, well, imagine you would want to machine learn this function. Like this is not realistic. You shouldn't do this, but imagine you wanted to. So you could be given many pairs of x1, x2, x3, and their maximum, and feed this into some neural network to train it. And like, of course, in reality, you would have much more complicated input data and the output somehow depends on it. But what I say doesn't really depend on how complicated this group action is or how complicated this map is. So it's fine to think of the case of the maximum map. Now, if you do this, your neural network will do something. You will approximate your function max, but it won't in general be group invariant. I mean, why would it? It doesn't know that it's supposed to learn something group invariant. So the questions that I'm interested in today are first, how can we make sure that this neural network is group invariant? How can we find group invariant neural networks? And second, does this actually improve the performance of the neural networks? Because if not, then what's the point of writing down architectures that are group invariant? And I hope we're going to arrive at a somewhat satisfactory answer to both questions. So I start with a brief bit of history. So that's previous approaches to group invariant machine learning. So if you don't know anything about the topic and you were given the task to learn a group invariant function, what you would probably come up with is data augmentation. So let's say you're given many training data points like this, x1, x2, x3, and their maximum. What you can do is enrich your training data, augment your training data by adding extra pairs into the training data. And the way you do it is you act on the input of your existing training data. So that's g times x1, x2, x3, and you leave the target as it is. And if your group is S3, you can actually do this for every group element in S3 because there are only 6 group elements. And so then if you had 1,000 training points before, afterwards you will have 6,000. So you can still do the training. It's not too many. Now, a fact that should be observed about this data augmentation is it still doesn't give you a guarantee that the function that's being learned is group invariant. And typically it won't be actually. It will be close to being group invariant, but not exactly. Now, the next two things, the next two approaches, they actually give you something that's on the nose exactly group invariant. So the first one is only for neural networks. And that works by restricting the weights of your neural network. And that was pioneered in this paper from 2017 called Deep Sets. And since then, so this is the very simplest example of this approach of restricting weights. So since then, there are many papers, many more complicated papers for other group actions. But let's look at this, because this is exactly for our case of the symmetric group acting on Rn. So that's good for us. So what you can write down is you can write down such a linear map L, which takes a vector and maps it to a sum of two things. So first, lambda1 times this matrix, which is all ones, times your vector, plus lambda1 times the identity times your vector. For some real numbers, lambda1 and lambda2, and those are exactly the weights of your neural network that you want to learn later. Now, you can easily convince yourself that this map that I've written down for any choice of lambda1 and lambda2 is group equivariant. So it has this equation here, L of g times x equals g times L of x. So to get something group invariant, what you can do is do the following. You can define a neural network like this. So I read it from right to left. You start with one of these layers L, and then you apply some non-linearity sigma, for example, ReLU or whatever. And then you compose more and more of these L's and more of these sigmas. So the notation is maybe a bit too short. The L's don't all need to have the same parameters. So every layer L has their own two parameters. So what I've written here is 3 layers L. That would be 6 parameters. And then you have to finish off with a pooling function. So some group invariant function from R3 to R. Because the last layer of L gives you something group equivariant, but to make it invariant, you need to apply this pooling. And here's one example of a pooling function. That's the sum function that just sums up the 3 entries. Now, this may again seem slightly silly because you have so few parameters, you only have 2. What you do in reality, if you want to build a neural network out of this, is you do the same as you do for convolutional neural networks. So you have many channels. So you have many parallel copies of these layers next to each other, and then they're concatenated and in the end averaged. So that's how you can build quite deep neural networks with many parameters, and it has been quite successful in many applications. One thing you may be maybe mildly concerned about is, well, those are only 2 parameters. It seems not very expressive, but one thing to say in that regard is there's a theorem which says that if you have any linear map from R3 to R3, which is S3 equivariant, then it must be of this form. So it's only governed by these 2 parameters. So I won't dwell on what that means for the expressivity of the resulting group invariant function, but yeah, you can prove some sort of universal approximation theorems. Then the last approach that I want to mention, again, is like the most basic version of a kind of technique about which many papers have been written by now. So there are many flavors and variations of this. So you start with some neural network, not necessarily group invariant, and then you define the following guy. You define NN twiddle, which takes some vector x1, x2, x3, and sends it to the sum over all group elements of NN applied to all translates. Yep, so we take one vector and then map it to the sum of 6 numbers. And the result is then group invariant. No matter if NN was group invariant or not, NN twiddle will be group invariant. And so then you use this in your gradient descent or whatever training scheme, and you train NN twiddle instead of NN directly. And you can convince yourself that n and twiddle really is group invariant, because if you don't plug in this vector x, but maybe g times x, then it will still be mapped to a sum of 6 things, just in a different order. Like you sum over the group elements in a bit different order. Right. One thing I should have asked, I should have said in the beginning, you're very encouraged to ask questions or make comments throughout the talk. So I'll just wait 10 seconds if anyone has any questions about this up to here. Okay, that seems not to be the case. Very well. So then we can dive into the hot new things, the new approach, group invariant machine learning through group invariant pre-processing. So that uses, the important thing here is that uses a function, say capital F, from R3 to R3, which is group invariant. So f of g times x equals f of x. Now this is different from the pooling function before. The pooling function was something that goes from our input space R3 to just the output space R. Now here, this is some sort of transformation of the input space. And the point of the talk is to tell you where do you get good maps F from. So this will come in a second. But right now you could think of a very stupid F, for example, the 0 map. F which sends everything to 0, this is perfectly group invariant. But you see now already at this step, if you take the 0 map, it won't help you a lot, because what you want to do is the following. Again, you start with some neural network, NN, maybe not group invariant. Then you define n and twiddle as this composition. So you pre-compose with F. And this will then be a group invariant function. So if you apply n and twiddle to g times x, just because of the group invariance of F, this is the same as n and twiddle of x. So this is group invariant. But you see, now if you take a stupid map like F the 0 function, then your n and twiddle is just the 0 map. So there's no chance it's ever gonna, or maybe it's not the 0 map, but it's just the bias of your neural network NN. So it's not gonna learn anything interesting. But yeah, if you found a good map F, then you can train this n and twiddle instead of NN. Now, one thing, one potential concern is, well, this map F, I haven't told you how to get it yet, but I will tell you in a second. It could be computationally quite expensive, and it would be bad to carry this along with your training and in every gradient descent step always apply this F. But it's actually equivalent if you once and for all process your training data and you apply F to all the inputs and you get f of x comma y, and then you just do ordinary training gradient descent on the data points f of x comma y. So then you don't have to compute this many times, but just once. Okay, but now, of course, the question you're all dying to have answered is how to get good F. And so the approach we take is using fundamental domains. So some subset U of Rn is a fundamental domain for some group action if it satisfies the following properties. It needs to be open and connected, and every orbit, so for all x, the orbit gx should intersect the closure of U. And if g of x, if an orbit intersects the interior of U, then this intersection must be unique. Those are the conditions for a fundamental domain. And if you found such a fundamental domain, you can define the following pre-processing map, capital F. Namely, you say that some point x is mapped to the intersection of the orbit gx with the closure u bar. Now, this is a slight lie. This is not completely well defined, because the third property of fundamental domain tells you that intersections of orbits with the interior of U are unique. But if you take something on the boundary of U, then actually there can be more than one intersection with U bar. So what I've written down is not strictly well defined. In general, there isn't a way to make it well defined. So we make it well defined on a case-by-case basis. And yeah, we're going to see that in the example section later. But first, also like a word of calming, maybe. You shouldn't be too worried about this, because this is only not well defined for points on the boundary of your fundamental domain. So if you have some randomly distributed data points with probability 0, they will lie on the boundary. So it's not often, you wouldn't expect this to happen very often. However, actually in one of our examples, every point does lie on the boundary. So yeah, it's worth thinking about it a bit. So here's an example of a fundamental domain in our toy example, where S3 acted on R3. You can take the open set U to be the one where the entries of the vector x1, x2, x3 are ordered in descending order. And I drew this on the left, this orange picture, this tetrahedron. Well, it's infinitely big, it stretches infinitely long, but I only plotted a finite part of it. This is U. Now you could choose other fundamental domains if you wanted. Namely, instead of x1 bigger, x2 bigger, x3, you could have some variations of smaller than or so. And there are 6 ways to arrange the coordinates x1, x2, x3 with bigger than and smaller than, and get a fundamental domain. And one other example, if you have your bigger thans and smaller thans a bit the other way around, then you get this green fundamental domain. And this big cube shows you that the 6 choices of fundamental domain, they tessellate all of R3, but except for this boundary in the middle. But let's say you define this fundamental domain the way I did it, so ordered in descending order. Then you get the following projection map, capital F. Namely, it takes the vector x1, x2, x3 and sends it to maximum, then the middle value of the 3 values, and then the minimum of them. And so notice the image of F lies in U bar. It doesn't lie in U, because if you have 2 coordinates of the vector which are equal, then it doesn't lie in U, but the function F still tells you what to do with them. So it can handle a vector 0, 0, 1, for example. Okay, but this is just some ad hoc example of a fundamental domain. So there's we have 2 general recipes to cook up these fundamental domains. And about the first recipe, I want to say almost nothing. And everything I want to say about it is in this paragraph here. So the first recipe are called combinatorial fundamental domains. And there is a paper by Dixon and Mahid which does the following. So for every subgroup of Sn, they wrote down an algorithm to compute a fundamental domain and projection map for the action of G on itself. So that, in other words, an algorithm to compute orbit representatives of this group. And oh, sorry, this should be the action of G on Sn, not the action of G on itself. So, okay. And then taking this algorithm, it's still a bit of work, but the main idea comes from their paper. Taking that algorithm, we generalize this to the case of G acting on Euclidean space as a subgroup of Sn, so by permutation of coordinates. Okay, yeah, but as I said, I would say almost nothing about this, but I would say a lot of things about this second approach here, the Dirichlet fundamental domains. And now the first thing, that was kind of a combinatorial thing. This is a very geometric thing, actually. So we're going to use the fact that if you have a subgroup of Sn acting on Rn, this acts through isometries. Namely, it satisfies this property here, that norm of x is the same as norm of gx. It is just because you're acting by permutation of coordinates. Now, if you take some generic point x0 in Rn, and I won't exactly say what generic means, just suffice to say, if you randomly sample a point of Rn with probability 1, it will be generic. So don't take a silly point like 0 or something, but most points will be fine. If you have such a thing, then you can define the following objects. So you can define U, which is the set of points which maximize the which maximize the inner product with your fixed point x0. So these angled brackets here, that's the dot product on Rn. And we want that x comma x0 is bigger than the product of all the translates with x0. Now, if you have such a thing, then you can define your capital F, just as I did on the previous slide, where you map a point x to a translate of x, which maximizes the inner product with x0. And again, the way it's written here is not well defined for things that lie on the boundary of U. So again, I have to postpone the explanation. How do we actually resolve this in special cases? But let's say, so in our toy example, S3 acting on R3, you take this point x0 equals 3, 2, 1, and you want to project some vector y1, y2, y3. Now what you get is, according to our definition of f, you have to maximize this inner product. You have to maximize y comma x0, which is 3y1 plus 2y2 plus y3. Now, in order to maximize this, you exactly have to reshuffle your vector y to put the biggest coordinate first and the smallest coordinate last. So what you find is, with this choice of x0, you get the following set U, or the closure of U, will be exactly vectors in R3, which are ordered in descending order. And so you should notice two things. First, this is exactly the same fundamental domain as from the previous page. On the previous page, it seemed like kind of an ad hoc thing that was special to S3 acting on R3, but actually it comes from this very general recipe that works for every group action on Rn. That's already nice. The second thing is, in this particular case, you actually don't have this boundary problem because you can always order a vector so that the biggest coordinate is first. And if there are two equal coordinates, this ordering map will still know what to do. So this boundary issue is not always a problem. Okay, so I'm almost ready to talk about the examples, but first I want to say a small thing about generalizations. And so first, let's stick with finite groups acting on Rn. Now, these can be very large. For example, S15 acting on R15. We're going to see this exact group in a bit later. This has lots of elements. So I looked this up before the talk. It has 10 to the 12 elements, roughly. Now, if you remember what I told you in the beginning about group invariant machine learning, the two approaches, data augmentation and averaging techniques, you can't really do it for such a big group because you would need to hold a lot of things in memory in your computer. And maybe a good computer can do it, but it's very computationally expensive, if possible at all. That said, the other thing that I mentioned, this restriction of weights, that's still possible, that works fine. And of course, our technique is also fine. That's the main point. Now, if you want to talk about generalizations, there are two things you can generalize. So either you can generalize the groups acting on Rn, or you can generalize the space that's being acted on. And I want to say a few words about both cases. So let's generalize the space that's being acted on. And a reasonable thing to generalize to is to take a complete Riemannian manifold. You can generalize this further if you want, but let's not worry about this. If you have such a thing on a Riemannian manifold, you don't have a dot product between points that are far away from each other. But the thing you do have is that you still have a distance function, so you can still measure distances between points. And then if you have a distance function, you can write down this set U, which the points, sorry, in Rn, well, it's not in Rn, it's the points in M. Which minimize the distance to some fixed point x0 in your manifold. Now this set you can write down for any metric space really, but if you want good properties of this projection map, then you need a bit more, and it's a bit difficult to formulate what properties your group action must satisfy. So let's stick with complete Riemannian manifolds. And so here's an example. I think the picture is actually not 100% accurate, but it's almost true. So this is a picture of the group action of SL2Z on the hyperbolic plane H2. And let's say you pick your point x0, this guy here in the middle. Then the fundamental domain U is exactly this black triangle around this point x0. And if you have like this green point x here in this triangle, you can translate this x around your manifold under the group action, and then you will get 1 point in each triangle. So all of these green little dots are translates of x, but there is exactly one of them which minimizes the distance to x0. That is, unless you chose a point on the boundary between the black triangle and a white triangle. So let's say if you choose here such a point, then the group action of SL2Z would transport this to another boundary point, potentially here, something like this. And you can see both of these guys have the same distance to x0. So again, your projection map capital F wouldn't really know what to do. So again, you somehow have to explain away this boundary issue here. So that's the first generalization you could make, generalize the space that's being acted on to manifold. The other generalization that you can make if you want is generalize to continuous groups. So not finite groups, but continuous groups called Lie groups. And there is already a word in differential geometry for fundamental domains with respect to these Lie groups, and they're called slices. So the definition will be slightly different. It won't be an open set anymore, but it will have this important property that orbits meet the closure, orbits meet the closure once. And if you're presented with a group action in such a slice, then you can write down the projection map as usual. But we didn't, so this is not in the paper. We have no experiments for any continuous group action. Right. Okay. So then I think it's time to talk about the examples. I have 3 little examples for you. So first, we'll start with an example where you can apply our proposal, but it turns out to be not useful. And you're going to see why it's not useful in this case. So the example is the rotated MNIST dataset. Rotated MNIST are 28 by 28 pixel images showing a digit, and they can be possibly rotated by 90 degrees, 180 degrees, or 270 degrees. So here's a little subset of this dataset. You see digit 3 first, and then a rotated thing could be 9, could be a 6. It's probably a 6 rotated a bit, and then a rotated 8. And this little green square has a meaning that we'll see in a second. Now, we want to machine learn this function or approximate this function h, which goes from R28 by 28. So this is like a map of pixel intensities into the integers. And it's the map which takes an image to the digit shown in X. And the point is, this is an example of a group invariant function that we want to learn. Namely, you have the action of Z4 on R28 by 28, exactly by these 90 degrees rotation. And the function h is Z4 invariant. You should predict the correct digit no matter how it's rotated. One thing to note is that, yeah, it's nice that Z4 acts on these 28 by 28 images, but for our scheme, it's kind of important to think of Z4 as a subgroup of the full permutation group of all pixels. So as a subgroup of S784. And you can write down the group action as a subgroup of this symmetric group, but you can imagine there's going to be some combinatorics needed because lots of pixels are moved to another place. So as a rotation of 90 degrees, it's very easy to understand. As a subgroup of S784 is a bit more tedious to write down. Okay, but so for this this little group action, we can now define the following thing. We can define a fundamental domain and projection as before by choosing the following x0. So I said before, choose an x0, and then you get for free this Dirichlet fundamental domain and the projection. Now there's a small lie here. This x0 is not generic, and yeah, maybe I'll point out why that's a minor issue. A theoretical issue that doesn't practically matter in this case. So if you choose this matrix X0, so it's 14 by 14 blocks, 4 of them, starting with 4 on the top left, ending with 1 on the bottom right. Then the set U, or the closure of U, as it was defined on the previous page, is exactly the set of all x's which maximize the inner product with this x0. And so these angle brackets, they're the inner product on R 28 by 28. So just if you have two matrices, the inner product is just multiply all the entries and sum them up. And so this is kind of reminiscent of when we wrote down the fundamental domain for the action of S3 on R3. Back then, we wanted to make the first coordinate of our vector the biggest, so that it's multiplied with this big number in x0. And now it's going to be the same thing. If we rotate an input image in order to maximize the inner product with x0, you want to make it so that the brightest quadrant is in the top left, so that it's multiplied with this big number 4 and not with these small numbers 3, 2, and 1. Now, I mean, a small issue that's caused by the fact that x0 is not generic is that it could happen that your image maybe has 4 equally bright quadrants. Within each quadrant, something completely different happens, just the average brightness is the same. And then this map wouldn't know what to do. It gives you something random. The reason that's not a problem in this case is that these are actually real-life data, and none of them have the property that there are 2 quadrants with exactly the same brightness. I mean, what are the odds? If you draw a random number, it's extremely unlikely that's going to happen. So this map F that's written down here is actually not a well-defined map, but we don't notice this on this rotated MNIST data set. So in this case, we don't really care about this not well-definedness. We do nothing to alleviate this problem. And so what do we get? Well, I already spoiled the surprise a bit by saying it's what we do is not super useful. And here you see the numeric proof of this. So let's look at this table. Everything in this table is a bit important. We compare 3 models. That's the first column. Just a linear regression, then a shallow MLP, multi-layer perceptron, just a neural network with 1 hidden layer, and then a deep convolutional neural network for image classification called SimpNet. That was just easily available, so we took that. And okay, so I mean, look at the first column of no pre-processing, no surprise there. The more complicated your model gets, the more expressive it is and the better the performance is. And now the last column is if we do the training and testing on the pre-processed data, so where we rotated each image so that the top left quadrant is the brightest. Now, it turns out this kind of helps the linear classifier. So performance increased by 11% or so. Very mild performance gain for the shallow neural network and no performance gain for the deep neural network. And the reason for that is that the symmetry group is very small. The symmetry group has 4 elements in this case. So if you have a deep neural network with many neurons that's very expressive, it's just going to learn this symmetry. But the linear classifier is not expressive enough. So that's really helped by our pre-processing. Excuse me. Okay, yeah, so that was a bit of the negative example. Our pre-processing doesn't make anything worse, but it also doesn't really help. But now we get to two mildly more interesting examples, to 2 datasets coming from string theory. So The first example, or example 2, is about complete intersection Calabi-Yau matrices. So I know many people already know what they are. And I'll give a super brief explanation of what this data set is. So there's some procedure to go from a 12 by 15 matrix, 12 rows, 15 columns, to get 15 polynomials, F1 to F15. Then if you have these 15 polynomials, you can write down the following subset of some complicated projective space. Is exactly the vanishing locus of all these polynomials. So the set where f1 of x equals 0 up to f15 of x equals 0. And this procedure, if you take the right input matrix, the resulting set would be a Calabi-Yau manifold, so some complicated geometric object. Now, I make it seem a bit easier than it is in reality. You can't take any matrix, you can't take every matrix, every real 12 by 15 matrix. It's actually quite restricted which ones give you Calabi-Yau manifolds. Up to some very precise notion of isomorphism, there are around 8,000 of these matrices which give you Calabi-Yau manifolds. So here's one entry from this list of 8,000 matrices. This is the first entry on the list. So I only drew what is it, 7 rows and 6 columns, and then it should be extended by zeros to the right and by zeros to the bottom. And yeah, so you see this matrix has many repeated entries. So in the list, all the entries are between 0 and 9. And it's a feature of this data set that every matrix contains many repeated entries. And here's an example. And so this will be a problem, as I hope I'll remember to say in a second. Okay, so far this is just the procedure to go from matrix to Calabi-Yau manifold, fine. Then there's some geometric thing, geometric invariant called the second Hodge number, which takes some Calabi-Yau manifold and gives you an integer. And these Calabi-Yau manifolds need not come from this matrix procedure. It can be any Calabi-Yau manifolds. And so the map that we want to learn is the map H, which takes the matrix and then turns it into a Calabi-Yau manifold and then computes the second Hodge number of it. So it's a map from R12 by 15 into Z for us. Now, it's a fact that H is invariant under the action of S12 times S15, where S12 acts by row permutations and S15 acts by column permutations. Now, the fact that it's invariant under the action of S15 is kind of easy to see, because you see, if you swap the columns of your input matrix M, that just amounts to reordering the 15 polynomials. But the vanishing locus of 15 polynomials is the same no matter of how you order them. To see that is also invariant under row permutations. To this end, I would need to tell you a bit more about this construction, but just take my word for it that it is. Okay, so this was the problem on the previous slide. And now comes the explanation of our group invariant preprocessing step. And so, as I said before, for these Dirichlet projections, you need to choose some generic x0, and then you get the fundamental domain and the projection for free. And so in this case, I mean, you could choose any x0, but here's a particularly nice choice that has a nice that's going to have a nice interpretation in a second. So if you choose this guy, so you start on the bottom right with 10 to the 0, and then you go line by line, up, and always increase the power of 10. So 10 to the 0, 10 to the 1, and so on and so forth, until you end with 10 to the 179 on the top left. So if you do this, you get the fundamental domain. Again, I just copied the definition from the previous slide. Oh, maybe before, maybe it was, I want to maximize an inner product. Now I say I want to minimize an inner product. But that's fine. Okay, so maybe slight change of less than and bigger than from the previous slide, but what's written on this slide is definitely fine. So we can define the set U, which now is the set of all matrices, which minimize the inner product with this x0. Now, if you were to ever compute this inner product of any matrix M with this x0 on a computer, it would be horrible, of course, because this 10 to the 179 is such a big number. It would be extremely annoying to compute. But the nice thing is you can rewrite this as follows. Just as before, when we had S3 acting on R3, what we really did was ordering our vector from big to small. So I say in lexicographical order. And it's the same thing here, actually. You want to order your matrix so that if you write line by line, one after another into a long vector with 180 entries, that this vector is lexicographically as small as possible. And now you see, so this you can achieve by some maybe sorting algorithm or comparing two vectors with respect to the lexicographical order. You don't need to have these very large multiplications. So the definition of U in the first line is extremely impractical. The definition of U in the second line is extremely tailored to implementations in Python, for example. So then your map F sends sends M to a lexicographically ordered version of M. So, for example, F of this 2 by 2 matrix is 0, 2, 3, 1. Notice you can't really lexicographically order all entries of your matrix. So you can't make this into the matrix 0, 1, 2, 3. This would be the case if you have a group action of the full symmetric group S180. But you have to make this lexicographically as small as possible using only row and column permutations. And this is the best you can do, 0, 2, 3, 1. Now, I said it, this lexicographic thing is much better than doing the inner products, which is true, but it's still not trivial to compute this function f. So the way we do it is, if you're given some matrix M, we apply random permutations, randomly chosen permutations, until the matrix M doesn't get smaller anymore. Now, is no guarantee that you actually find a global minimizer this way, because we choose random permutations, and if we can't make it smaller anymore for some time, then we give up. But it turns out it's sufficient in practice. We're going to see it actually helps the performance. And you may think, well, this is a very silly thing to do. Why didn't you think a bit harder and come up with a better way to compute this f? Well, the thing is, it's unlikely that it's possible to compute this f in polynomial time. Because if you were able to do this, you would be able to decide the graph isomorphism problem in polynomial time. So given two adjacency matrices of two graphs, the graph isomorphism problem is to decide whether they're isomorphic or not. And what you can do is you can bring these matrices into this canonical order, into this lexicographical order. And then if the ordered matrices are the same, the graphs are isomorphic, and if not, they're not. And it would be surprising if you can do this in polynomial time, but it's not proven to be impossible. Okay, so let's look at the numbers. So what do we get? So here on the left, we have, it's a bit unfortunately ordered, the table, apologies for that, but we have 3 models. We have MLP, which is a neural network with a few hidden layers. We have Inception, which is a deep convolutional neural network adapted to this particular problem. And then G-invariant MLP, that's a group invariant neural network using this restriction of weights technique that I explained in the beginning. Okay, and so the next column, original data set, kind of has the same result as on the previous page. So we see that the smaller models are helped more by the pre-processing than bigger models. So this small MLP gets plus 30% accuracy by our pre-processing. And the Inception, so this very deep neural network, actually doesn't get any significant increase. This is just within the standard deviation. So basically no improvement. So what we did is we had this hammer of our amazing group invariant pre-processing. So we were looking for a nail. So when is it actually useful? So what we did is we took the original data set and applied random permutations, like random row and column permutations. The Hodge numbers still stay the same. So in theory, you would want some way to get the same accuracy on this randomly permuted data set. And so here's what we found. Like the G invariant multilayer perceptron doesn't get worse. In fact, it gets slightly better here, but again, not significantly better. But this is group invariant, so it doesn't care about permutations. And the MLP and the deep neural network, they're both helped by our fundamental domain projection, actually here quite significantly. So for this particular problem, which is slightly contrived, we find that the pre-processing is actually useful. Okay, and then so I'm almost out of time. So I'll be very brief with the last example. The last example are Toric varieties, so Calabi-Yau manifolds coming from reflexive polytopes. And let's not dwell on how you go from a 4×26 matrix to a Calabi-Yau manifold, but you can do it. And then we are interested in this function here, so which takes a matrix to second Hodge number of the corresponding Calabi-Yau manifold, and choose your x0 as before, and then you get the u and f with this lexicographical order thing, just as before. And so we can compare the following models. We have MLP with reduced input. This is a thing from the literature, but I should be honest, they solve a harder problem than us. So they were at a bit of a disadvantage. But anyway, for this particular problem, they're not doing so well. And then we have a deeper MLP, and we have an invariant MLP again. So this thing with the restricted weights. And so here you can see it's actually useful, even without this contrived task of randomly permuting first. The best you can do is to take a model that's not group invariant and then apply this pre-processing to make it somewhat group invariant. Okay, so I think that was all I had to say. And oops. Is that it? Sorry, 1 second. Right, yeah, that was it. So thank you very much for the attention.